Hello, good afternoon. Can the people in Zoom hear me? Give me a thumbs up or thumbs down. All right, thank you, Sonia. In case you have any questions, just feel free to ask. We are still 2 minutes away from 4 o'clock, so I managed to get this computer working. Yes. So when I say lecture 3 reading this, I really mean you read that particular section after the lecture, because there are many nice examples in the book, but I can only go through a strict subset of them, which means I cannot go through all examples. But some of the examples you can treat as practice problems with solutions, so that's very nice. So you should read. I will go through all the theory, but I don't have time to go through all the examples in the book. I will only go through a few. Okay. All right, so it's 4 o'clock. So let's get started. Good afternoon, everybody. I hope that you're still with me. So today, this is lecture 3, and your reading assignment is section 1.4, as is detailed in the information sheet. And I just want to announce that homework 1 will be out today. By the end of today, I'm still finalizing a few things, but it is due on 27th of January. So you have about 2 weeks to do it. I suggest you get started ASAP because it is not short. Okay. So you are free to talk to one another, and you are free to talk to me in case you don't know how to do a certain thing. I'm very happy to give you hints and to help you, but you need to have the initiative to talk to me. There are 10 questions altogether. It's not short. Average, how long will it take to do it? If I do it, it will take 5 minutes. But if you do it, I don't know, it depends on how much you understand the lectures. Because yeah, they are just questions that are rudimentary if you understand the lectures. But if you don't, then you have to revise the lecture concepts before you can do the problems. So nothing is trickier, okay? Yeah, but maybe unlike previous offerings of this class, previous professors don't ask you to turn in homework. But I think this homework turning in business actually will help you understand the material better. So let's all do it, okay? It's more work for everybody, like my graders, but then I think it benefits you. So there are some questions. I will tell you the exact time. I'll tell you the exact time later on, okay? Is it? 27th of January, yes. Okay, we can be very flexible. 1 more week? Yeah, no problem. Yeah, I'm very flexible. Yeah. Anything is fine, yeah, as long as you do it. Okay, let me just get started. Are there any questions about homework? As I said, there are 4 homeworks, right? But the top 3 are taken, okay, in the computation of the final homework grade. So last time we talked about conditional probabilities, and basically in this area, we have 2 events, and events are subsets of the sample space. This is the sample space, just to recall. And now, what does it mean for us to condition on event B? Okay, so that is event B, and that is another event A. Conditioning on event B means that we are living here. Instead of living in omega, which is the big sample space, we live in B, all right? And what is of interest to us now is the conditional probability of event A given event B. And I will illustrate this with a lot of examples. I've already done so last time, but we will provide another example this time. And this is the formula that I tell you that you have to commit to memory, okay? So we have already talked about this formula last time. Now let's try to do an exercise, all right? So there are 2 teams, and this is from the book. One of the team is a conservative team, and let's say it is team C, and this conservative team succeeds with probability 2/3. And we have another team that is called the whatever innovative team, and it succeeds with probability something else. Okay, so that is the innovative team. N succeeds with probability 1/2, and we know that at least one team succeeds with probability equals to 3/4. So those are all the information that we have. So let us try to express this mathematically and then answer a few questions. So let us use SS to denote the event that both succeed, SF to denote the event that the first team succeeds and the second team fails. And say FS fail succeed means that C fail and N succeeds and FF both fail. Okay, so these are all the possible events, and from the information that we have here, okay, from the information that we have here, we know that the probability that team C succeeds is 2/3. So the probability that team C succeeds is the probability that both succeed plus probability of team C succeeding plus and team N failing. So you look at these two guys here, these two events here, C succeeds in them, right? Regardless of whether N succeeds or not. So that is equal to 2/3. This one comes from this one comes from here. This event corresponds to exactly this. Does that make sense? Does that make sense to everybody? So there, SS plus SF means that team C succeeds. I don't care about team N. Team N can succeed or fail. So that is represented by the second label there, SF. Okay, that is represented by the second symbol here, S or F here. Doesn't matter. Okay, so now we also have another additional information that the team N succeeds is half. So we have SS plus probability, this is symmetric, right? Is equal to 1/2. And finally, okay, so this one comes from, obviously this one comes from here. The innovative team succeeds with probability 1/2. And here we have this information here. This translated to mathematics. And finally, at least one team succeeds. At least in mathematics means at least, right? At least one team succeeds means one team succeeds or two teams succeed. That's the meaning of at least. Okay. So what is this event? Well, that is probability both succeed or team C succeeds, the other fail. Team C fails, the other one succeeds. That is equal to. Huh? Okay, let me explain this. Because you are given the information that C succeeds is 2/3. Okay. Now, C, what is the meaning of C succeeds? C succeeds could mean C succeeds and the other one N succeed, or it could mean C succeed and the other one fail. So these two contribute to this one here. Can you understand now? Okay, cool. Yeah. So the last event here is that at least one team succeeds. At least means you could have two succeed here, or one team succeed, the other one fail, which is these two guys here, equals to 3/4. Understand? Very good. Interactive. However, we note that the probability of every event happening, what does this have to sum up to? Equals to 1. Perfect. So now we have this system of equations. All right. We have this system of 4 equations in 4 unknowns. So in principle, we should be able to solve. Okay. Now there's a fast way to solve this and there's a slow way, but let me show you the fast way. Okay. You can put this in a matrix and do inversion if you wish, but no need. You see these three terms are common here. So I can figure out that PFF is 1/4 straight away. Right? Because I just take this equation minus this one, and I'm left with just the PFF here. Okay, so now I have PFF done. I've gotten it. So the rest you can also do elimination. Okay, and that is beyond the scope of this class, how to do getting of all these numbers from the equations. So I will not belabor the point, but if anyone wants me to explain how I got these numbers from the equations, I'm happy to do so. Let me do one more for you, okay? Which is this one here. How do I get SF equals to 1/4? Okay, so let me see. Okay, so here, okay, you see that here, SF, you look at these two equations here, these two here. Okay, what do they differ by? You see that there is a lot in common. This is common with this is common with this, and only the SF is not common. So I take this equation, let's call it equation dagger, minus equation 2 dagger. So 3/4 minus 1/2 is what? 3/4 minus 1/2 is exactly 1/4, right? That's how I gotten this. All right, just by inspection, you don't need to do too much work. All right, you can do more work if you want. Yeah, so you can do all the other work to get all the other numbers, but that's just algebra and I won't belabor the point. And just to answer Tan Yong, I cannot see the last word, question in the Zoom chat, where you submit the homework, you submit it in some folder in Luminous. I will let you. Okay, I will upload the homework very, very soon. I'm just making sure there are no typos in the homework before I upload them. Okay, so by the end of tonight. Yeah. Okay. Try not to disrupt me too often, otherwise I cannot think what I want to say. Okay, so the question I want to pose here is the following. Given exactly one success, okay, what is the probability it was designed by N? It was N who succeeded. Okay, so let's try to translate this English into math. So we are given, that means we are living in the space of one success. Okay, we are only living in the space of one success. It cannot have that two are succeeding. So we are interested in, okay, Fs, okay, this means that N succeeded, and C failed. Remember our convention, okay? Now we are conditioning on exactly one success. So this is one success, this is another success, understand? So that is our event B, this is our event B, and this is our event A. So we are living in this universe that one team succeeded. We discard the events that no team succeeded and two teams succeeded. We are only interested, someone told me that one team succeeded. All right. So now let's calculate this using the formula. So this is P of Fs intersect of Fs SF divided by the bottom. P of Fs plus P of SF. Right? So that the bottom here can be separated into this and that. And the top is basically the intersection. But this guy here can be simplified. Okay, this guy here can be simplified significantly because the numerator here is nothing but P of Fs. Because if you take P of this event here, intersect this event, you're looking at the common part. And the common part is just this event Fs. This is the common part. You discard this part because you're looking at the intersection. Okay, so you're left with this number here, this ratio here. And now it's a matter of plugging numbers in. Okay, so Fs is 1/12 from the above, 1/12 here. And the bottom is, okay, you have this repetition of 1/12 from here. and SF is 1/4, and that 1/4 comes from here. So we are just copying numbers, and you can plug this in your calculator and you get 1/4 as desired. Okay, so that's an application of the formula. Any questions? All right, so we need to know how to remember the formula and apply the formula. Okay, any questions on this from the Zoom people as well as from the people in the live audience? So here we are living in the space of exactly one success. What is the chance that it was N who succeeded instead of S who succeeded? Oh, sorry, instead of C who succeeded. So homework question for you, do it by yourself. Given exactly one success, what is the probability that it was C who succeeded? Okay, do it. Okay. There are two ways of doing this, all right? So I want to now introduce, if there are no questions. Yeah, so, okay, why is the denominator this? Now, remember that the denominator is equal to probability of Fs and Sf. So these are two different elements in the sample space. This can be decomposed into probability of just this element plus probability of that element. It can be split up. Okay. So I have a lot of similar questions here. So the probability of these two elements here is just nothing but the probability of one of the elements plus the probability of the other element. So for example, okay, let me give you an example. You toss a 6-face die, the usual dice. What is the probability that it comes up 1 or 5? Well, that is nothing but the probability that it comes out, it comes out 1 plus the probability it comes out 5. Is that simple? Do we need to put this yes and no? If you are very pedantic, you put the curly brackets. If you are not, it's okay. Don't need to put the curly brackets. It's understood. Okay. So for the Zoom people, is this clear now? Why is the denominator given by the sum? Is it clear now for the people in the audience here? What's your name again? Yeah. Paul Yu. Oh. Oliver is easy. Oliver is my son's name. Okay. Now I know Oliver. Very good. Is this clear, Oliver? Very good. Okay. Is it clear? So the denominator is the probability of these two elements. The probability of the two elements is the probability of one element plus the probability of another element. It's just like I ask you, what is the chance that if you throw a dice, the outcome is 1 or 5? Well, that's the probability of 1 plus the probability of 5, right? So we are just using this simple rule here. Okay, thank you very much. Now, the next thing I want to talk about is the so-called multiplication rule. We saw that the probability of A intersect B is equal to probability of A given B, probability of B. Now, this comes about because we wrote probability of A given B as probability of A intersect B divided by probability of B. So now I'm just multiplying both sides by PB. Okay, so we get this in case it's not clear. So we can consider doing this inductively, consider doing this for n events. All right, so the probability of A1 intersect A2 intersect ... intersect AN. So here we are only considering 2, but nothing is stopping us for considering n. So that's nothing but PA1, PA2 given A1, PA3 given A1 and A2, and so on and so forth up to P of AN given A1 intersect ... intersect AN minus 1. So if this is very confusing and very scary, you just consider 3 events first, A1, A2, A3, and then you can break it up into this. Then you can do it consecutively. So basically, this is a rewriting of this, okay? Then you have one further event, A3, but you need to condition on the previous things, which is these two things together, which is A1 intersect A2. Okay. Now this looks a little bit complicated, but let me illustrate this through another example to make it clear. Okay. Now you draw 3 cards from a standard 52 card deck without replacement. So we want to consider the probability that none of the cards is a heart. How do we do that? So we draw 3 without replacement. We take 1 already. We don't put back. We keep in our wallet. Then we take 1 more. And then we keep in our wallet. And then we take 1 more. We keep in our wallet. So we don't put it back. Now, in a standard 52 card deck, right? How many hearts are there? 13 hearts, right? 13. From ace of hearts to the king of hearts. 13 out of 52 are hearts. So what is the chance that you pick 3 cards, none of them is a heart? Now for this to happen, let us define some mathematics. AI is the event that the I card is not a heart. And we are interested in I running from 1, 2, 3. A1 is the event that the first card is not a heart. A2 is the event that the second card is not a heart, etc., etc. All right. So what we do, what is this probability that we have just written down and we are interested in evaluating in terms of the ace? Well, that is nothing but probability of first one not a heart, and second one is not a heart, and third one is not a heart. Can you interpret the probabilities here? None of them is a heart. That means all the a's must be simultaneously satisfied. A1 intersect. Intersect means and. All right. None of the cards is a heart means the first one is not a heart, second one is not a heart, and third one is not a heart. Cool. All right. So now we can use the multiplication rule, or what we call the multiplication rule, only on the first 3. So you see, this is nothing but P of A1, P of A2 given A1, P of A3 given. Okay, a lot of people will make a mistake and only put 2 here, but it's A1 intersect A2. A1 and A2 here. Don't make the mistake of dropping A1. Okay, you need to put it here. And if there is an A4, then it is A2, A3 here. You need everything. Okay, if there's an A4, but there isn't here. I just want to remind you, okay? Let me just get rid of this. Okay, so now we are going to evaluate each one of these probabilities individually. What is the chance of A1? That means the first card is not a heart. Come on. But since you don't put back the cards, yeah, the number of cards you take from decrements each time. Indeed so, David. Indeed so. But the sample space is still the same, actually. The sample space is still the same. Nevertheless, let us try to do the question just by logic. Okay, both these answers are correct. It's 3/4, or let me put it more explicitly as 39 out of 52. And 39 is obtained by 52 minus 13 out of 52. Is it clear? So there are 39 non-hearts cards among 52. Okay, so now we have to do multiplication. Now we take out 1 card already. How many cards are there left? 51 left, right? So we have to put 50. What's the chance that among the 51, we don't pick a heart? 38. Right, 38 left. All right, 38 are non-hearts. Then you see the pattern. After you have taken 2, how many cards do you have left? You have, so this, what is the meaning of 38, right? 38 is basically 51 minus 13. Just to write it more explicitly, okay? Now we have 50 left, right? After we have taken 2 cards, we have 50 left. So 50 minus 13 is how much? 37, I guess. So this is 50 minus 13 out of 50. So this is whatever it is, okay? You can use a calculator, but the principle is more important. So here, what we are doing is we are conditioning on a certain event here. We are conditioning on the event that we only have 51 cards left, and the first card we picked was not a heart. All right, so we have 13 hearts left in the 51. Okay, so we have 38 non-hearts in the 51. And so we have this number here. Right. Any questions? Any questions? Am I going too fast, too slow? Pardon? Oh, yeah, second one is thank you very much, typo. Good, good. This gentleman is very much listening. So I don't bother to calculate this out. The principle is more important, okay? If we type on a calculator, we'll make mistakes. Any questions here? The important thing is you understand we are conditioning on this. So I want to mention here, for example, when we are conditioning on this, what are we actually conditioning on? I want to make this notes. We have 50 cards left, and among these 50 cards, there are 13 hearts remaining. That is what we are conditioning on in this particular event. Is that absolutely clear? So we are left with 50 cards and 13 are hearts, the rest are non-hearts. What's the chance that we pick a non-heart? Well, it's 37 out of 50. All right. Cool. Okay. Yes. So as I mentioned, if we have one more, it will be the following: P of A4, the line. This is read as conditioned on, not the line. Conditioned on. A1 intersect A2 intersect A3. Now this can also be written if you want as A3 intersect A2 intersect A1. So it doesn't matter whether you write 1, 2, 3 or 3, 2, 1 because it's you can rotate it around. Okay. Is that clear? This is the fourth one. This line is called condition on. Don't say line. You sound very not so professional. That means if we condition on a particular event, we are living in that space. All right. So like if we are conditioned on A1, A2, we know at this point in time, we have only 50 cards left. We started off with 52, remember, but we didn't replace. And among these 50 cards, there are 13 hearts remaining. Is this clear? Okay, that is the meaning of condition on. Cool. Do we have any questions? No, we don't have any questions in the Zoom. Okay, so now I want to go on to the topic of total probability theorem. Now we are ready to talk about this. And Bayes rule. And we'll supply all this with lots of examples. We'll supply all these terms with lots of examples. Okay, so the idea, let me draw a picture first. Now, sometimes we want to evaluate the probability of a certain event, but this is very difficult. Now, sometimes it's very difficult to directly compute this. And we'll see some examples of this. But it's easier to compute the probability. This is difficult. It's easier to compute the probabilities of B given AI for some other events AI. Okay, for some other events AI. So it's easier to actually condition on some other events before we do the calculation of PB. All right. So the picture is as follows. You have this large sample space. Okay. And that's what we call omega. And this sample space can be split up. Can be what the mathematical term is called partition into A1, A2, A3, A4, for example. And now you're interested in the probability of a certain event, and that is event B here. Now, it is much easier to compute in some applications B intersect a particular A3, B intersect a particular A1, B intersect A2, and so on and so forth. So the total probability theorem, okay, says the following. Okay, let A1, A2 dot 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 AN be disjoint subsets of the sample space. Disjoint means AI intersect AJ is the empty set. So as you can see from this picture, the A's don't overlap with one another. At least that's how I meant to draw it. Let A1, A2, AN be disjoint subsets that form a partition of the sample space. sample space omega. Okay, so what is the meaning of partition? Partition means you take the union, then they are the whole space omega. So it is exactly this picture here, where the A1, A2, A3, they have nothing to do, there's nothing in common. But if you take the union, you get the entire sample space. Okay. And we assume that each of the PAIs are positive for all I running from 1 to n. Then we are interested to compute the probability of an event B. Well, that is nothing but P of B intersect A1 plus P of B intersect A2 plus ... P of B intersect AN. So the picture is as follows, all right? So P of B is exactly this purple thing, purple event, all right? So we are saying that, okay, in order to compute the probability of B, why don't we take an approach that tackles P of B intersect A1 first, this part first, okay? Next, we tackle this part, okay? P of B intersect A2, all right? Part by part, we are like engineers, we do things slowly, okay? And this is the fourth one, PB intersect A4, for example, and here. So we do it slice by slice. Maybe we have one more in between, which is this one here, A3, which is over here. So we are splitting up this probability of B into disjoint parts that intersect with each of the AIs, okay? So it's very important that the A's are disjoint and they form a partition of the sample space, which means they span the entire sample space, omega, or I think this book calls it S, okay, whatever. Right, so this is usually very handy, very useful, and we need to know how to use it. So let me illustrate this very abstract or somewhat abstract concept with an example, okay? So let us roll a four-sided dice, okay? If the result of the first roll is 1 or 2, roll one more time. So the maximum number of rolls in this game is only 2. So we roll the dice, a four-sided dice, equally likely. If the result is 1 or 2, we roll one more time. If the result is 3 or 4, stop the game. Cool? All right. So what's the probability that the sum is 4? Okay, this is actually not very easy because a lot of things are happening at the same time. You could roll once or you could roll twice, right? If you roll twice, you need to add 2 numbers. If you roll once, you might be super lucky and you roll 4 and that's it, done. And you are happy because the sum is exactly 4 and you can answer this question. So this is not an easy question to answer, all right? And let's try to be a bit more formal here. In order to use the total probability theorem, let AI be the result of the event that the result of the first row is equal to I. Here I is equal to 1, 2, 3, or 4. So this is a partition of the sample space because the first row must be either 1, 2, 3, or 4. It cannot be 5. So it's just like this picture here. Okay, I roll the first time. I roll the dice the first time. It must be here, 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 or here. And this cannot overlap. You cannot roll and then, 1, 2 appear at the same time. No such thing, right? And it must be 1, 2, 3, or 4. So it's a partition of the sample space. Okay, this is a partition of the sample space. Can you see that? We've row. And now the natural thing to do is to condition on each AI. But our event of interest is B. Actually, the question is the sum is at least 4. Okay, so that's the actual question. Sorry, typo initially. So B is the sum of the 2 rows, sum total, sum. Let me just say sum is at least 4. Okay, sum is at least the question, sum is at least 4. You can do the question, sum is exactly 4 if you want. Okay, so these AIs are a partition of the sample space. AI for I equals to 1, 2, 3, 4, partition the sample space. And so we can use the law of the total probability theorem. Okay, so AI intersect AJ is equal to empty set, I not equal to J. That means the AIs have got no overlap. And furthermore, A1 union A2 union A3 union A4 is the entire sample space omega or S, whatever. So this checking here, the fact that we check this, okay, allows us to use the law of total probability, the total probability theorem. Okay, we need to do this check either mentally or writing it down. Any questions? Oliver? Now I know your name. The first toss must be either a 1, 2, 3, or 4. So that partitions the sample space, regardless of what the second toss happens. The first toss must be 1, 2, 3, or 4. And if you have a 1, you cannot have a 2. That's what this means here. And the first toss must be 1, 2, 3, or 4. That's what this mathematical thing means. Yeah. You need to have 1, 2, 3, or 4 because this is only a 4-sided dice. This one? This one intersection. Intersection means this one, the middle here. Union means everything. Okay. I think it's very important to revise these concepts of union and intersection. This is the union. Okay. Union means all, everything. Intersection means only the middle part, only the common part. Okay. Yeah. I'm happy to explain all these things because the fundamentals are super important. Anyone wants me to go a bit slower to explain this? Nothing in the Zoom chat here. Let me move this. Okay. We are all good? Cool. So now let us try to compute the probability of B. What did we say? Okay. Now, the probability of B, as I mentioned, we can use this formula here. Okay, that is the law of total probability. Okay, so that is that plus here, let me write down the middle part, the probability of B intersect A3 plus this, right? And this is A4. Right, so this is nothing but the law of total probability copied from above because the A's form a partition. Now, this is still not very amenable. So let us consider by using Bayes' rule, we can write this as PB of A1, P of A1. So this is just nothing but an application of Bayes' rule. P given A2, P of A2 plus P, B given A3 or condition on, last time I said condition on, plus P, B given A4, P of A4. Right? So remember that here what we are using is Bayes' rule or conditional probability. P of B given AI is nothing but the intersection AI divided by P of AI. So now you multiply the P of AI over on this side and you get the product here. All right, for each I. Is this step clear? Oliver? Unfortunately, I only know one name. Is this step clear? I'm using this formula 4 times. Yeah, because you see here, I move this over to this side and this becomes the product here, the multiplication. 4 times, can you see? Okay, is that clear to everybody? Yeah, okay, good. Okay, there's no need to copy anything unless you really want to copy because this is an example in the book. All right, so probability of each AI is what? Say probably A1. What is the chance that the first toss is 1? 1/4. Yes. So this is also true for the second 1, 2, 3, 4. by symmetry. I'm not going to belabor this point. But the rest of the probabilities, P of B given AI, they are harder. Okay. So what is probability B given A1? Oh, this is not so easy. Let us think what is this story. I also had to think. Okay, so let me write this down in English. Probability that the sum is at least 4, given that the first row yields 1. So if the first row yields 1, what is the chance that the sum is at least 4? What do I need for the second toss to be? 3, 4, right? 3 or 4. So this is equivalent to probability that the second row is either 3 or 4, given the first row yields 1. Agree? Yeah. So what is the chance that the second row is 3 or 4? I think you know that this is 1/2. Or just to be more pedantic, this is 2 out of 4. Right? Okay, so we can continue this exercise. Probability of B given A2. Oh, okay. Now, so the sum is at least 4, given that the first row is 2. Oh, so that is a story now. Okay. Then let me copy this. Okay. The sum is at least 4, given that the first row yields 2. So what needs to happen on the second row? What needs to happen? Now let us think very carefully. What needs to serendipitously happen? Right. So the second row must be what such the first row yields 1, such that the sum is equal to 4. The second row is either, come on. First row yields 2. So if I want the second row to be at least 4, then I need if I want the sum to be at least 4, then I need the second row to be 2, 3, 4, right? Either 2, 3, or 4. And this has 3/4 chance, right? Now, let us compute P of B given A3. Once you have 3, right, you are not going to roll a second time. So you have no chance of getting 4, or at least 4, 0. Now, P of B given A4. Oh, once you roll 4, you also don't roll one more time. But you have at least 4 already, right? 4 is at least 4. So this probability is 1. So in this particular example, right, you see that actually the probability of B is very hard to evaluate without conditioning on what is the first toss. That is the utility of the total probability theorem. If we want to get our hand on this, it's very difficult. But if we want to get our hand on each one of these individual things, it's not so difficult if we are systematic. Oliver, understand? No? All right. So if I ask you what is the chance, the probability that event B happens, the sum is at least 4, you are at a loss because you do not know what the first toss is. If you know what the first toss is, you are kind of in luck because you can condition on the first toss being something, and then you can add on something to understand when the sum is at least 4. And that is precisely the intuition that we have here. We condition on the first toss being 1, on 2. Then we can write this in English, right? If the first toss yields 1, and I desire that the sum is at least 4, then I need that the second toss is 3 or 4. Yeah, and 3 or 4, there are 2 outcomes here out of 4. That is 2 out of 4. So I do think systematically I condition on A1, A2, A3, A4. This is easier. All right. Here similarly, and similarly. So we partition the sample space into 4 parts. And then based on each of the 4 parts, I look at when I am going to get sum of at least 4. So I did 2 very carefully here, P of B given A1 and A2. The rest I didn't write down so carefully. But in case anyone wants me to explain the 3 and the 4, I'm happy to explain why it's 0 and 1. Yeah, perfect. You get me. A4, you don't roll anymore, but the first toss is already 4, so you're at least 4, probably 1. Yeah, done already. So now we put all the pieces together in our formula, which is this formula here. Okay, So I'm going to bring this formula down here, and then we're going to plug numbers in. And I'm not very careful in plugging numbers in, so we need to copy carefully. 2 over 4 times 1 over 4 plus 3 over 4 times 1 over 4 plus 0 times 1 over 4 plus 1 times 1 over 4. And this is whatever it is. Okay, so that's the way to do it. You see that if you do this in a naive way, you try to force the issue and to compute probability of B is very difficult. So we need to split up the sample space into A1, A2, A3, A4. Okay, now I have a question. So the two rows, David, the two rows are independent. We can assume this. So now, when we say this, okay, for example, probability of B given A1 is this one here. We rewrite the second row, the story of the second row here. Okay, right. And then the second row is nothing related to the first row. So we can actually drop this part here. And then we look solely at the second row. What is the chance that the second row is 3 or 4? But the second row only has 4 outcomes, 1, 2, 3, 4. 3 or 4 out of 4. There are 2 outcomes out of 4. So it's 2 over 4. So that's how I compute the probability of the rerow. David, is this clear? You can deliberate on this a little bit, okay? Now I will answer Jillian's question first. Prof, can you explain how to get this one equal to 0? Now, we need to understand the story, okay? The story says that if the result is 1 or 2, we roll one more time. If the result is 3 or 4, we don't roll anymore. So Jillian, if the outcome of the first toss is 3, we don't roll anymore, and the sum is equal to 3. The sum is equal to 3, and this is, i.e., it is not at least 4. So the probability is 0. Jillian, understand? So because here, if the first toss, first row equals to 3, implies we don't roll again. So we are stuck with 3. Jillian, understand? Okay. Everyone here understand? Okay, I'm happy to go very slow because I'm almost done for today, except I want to explain one more thing. Any questions? Would drawing a tree diagram be feasible? David, this is a brilliant suggestion. However, I do not know what tree diagram you have in your head. If you could draw a tree diagram on paper and send it to me, I will tell you whether it's feasible or not. Because I think in terms of this picture here, all right, and we are partitioning the sample space into the basically first row equals to 1, first row equals to 3, and so on and so forth. So this is the very straightforward one layer tree diagram. Okay. So let me go to the last thing that I will talk about, and that is Bayes' rule. And we will revisit this again at the start of next lecture, because I always like to repeat what I talked about the last time, the last part of the last lecture. Okay. So again, we have the scenario that say A1, A2, all the way up to AN are disjoint events of the sample space omega and form a partition. So the exact same picture. So in the case, sorry, it's not going to look good. So here is our sample space, and we can split into 3 parts, for example, or 4 parts. A1, A2, A3, A4. That's the meaning of they are pairwise, they are disjoint, and they form a partition, okay? I've already written this. And let's assume that P of AI are positive for all I. Okay? So now, oftentimes we want to say something about the probability of AI given B. Okay? B is another event with probability of B bigger than 0. And we want to say something about the probability of AI given B. So the picture is as follows. We have a particular event B here, all right? And we know this is event B. We know that we are inside we are inside this blob here, we are inside this circle here. What is the chance that we are also inside, say, A2? Okay, here. Right, this will be best illustrated using an example. But the formula that you should internalize is as follows. You have already known this formula, P, the conditional probability formula. This is the intersection divided by P of B. This is some formula that you understand from conditional probability. Okay, this is something that you already know. But now, this is something additional that we just talked about, the total probability theorem, which is that the bottom can be written in terms of probability of B intersect A1 plus ... plus probability of B intersect AN. This is the total probability law, total probability theorem, if you wish. Okay, and this can be written in yet another way, which is AI P of B given AI. So here we are again applying conditional probability on top, okay, divided by conditional probability below, which is P of AI give AI, P of B given A1 is 1, plus ... plus P of AN, P of B given AN. Now, this all looks a little bit complicated, all right? That's why we need to illustrate things with examples. Now, so oftentimes we are given, or we can calculate what is the probability of B given AI, right? For example, here, we did a lot of good work computing probability of B given A2. We did a lot of good work here. And I explained to Jillian why probability of B given A3 is 0, and you can infer why probability of B given A4 is equal to 1. This direction is usually easy. But the reverse direction, what is the chance that AI, what you're conditioning, what you were initially conditioning on, you're interested in this event, condition on a particular observation, which is B. So for this, you need to flip things around, flip it around by using the conditional probability formula, and then the total probability formula in the bottom. Okay, but the total probability formula, each one of these terms here can be applying the conditional probability formula. Okay, remember the conditional probability formula is this guy here. So we apply it to this intersection. So we have P of A1 and the conditional, which is PB given A1. So we're just flipping things around. All right, so we have to be very familiar with this flipping. Okay, so this is a bit abstract. Now we need to illustrate this using an example. So A is the event that an aircraft is present in the sky. Okay, and B is the event that the radar generates an alarm. Now, if an aircraft is present in the sky, you hope that the radar is functional and generates an alarm to alert your armed forces to get ready, all right, because you might be attacked. But sometimes your radar may be faulty, all right? So, all right, let me give a few numbers. Well, we are not at war every day, so the chance that an aircraft is present is 0.05, okay? Well, conditioned on the fact that there is an aircraft present in the sky, your radar is functioning most of the time, 99% of the time. So if there is an aircraft in the sky, that is, you are conditioning on this guy here, there's an aircraft, then we know from experience that our radar is 99% accurate. For example, if you have COVID, what is the chance that the PCR test is positive? Well, almost that, all right? Okay, so these are two pieces of information, but we need one more piece of information. Suppose there is no aircraft in the sky. That is called A complement. There's no aircraft in the sky. Now, what is the chance that there is a false alarm? The radar sounds. Okay, these are fictitious numbers, but let's just play around with these fictitious numbers. So, oh, your radar suddenly gives an alarm, even though there is no one trying to kill us. All right. So this is a false alarm. Now, but these are just fictitious numbers for us to do some calculation. But as you can see, these are quite natural to put down. But now I want to ask you to use this formula to compute the probability that there is an aircraft in the sky, given that, okay, I can observe that my radar actually emitted a sound that generated an alarm. I know from hearing that the radar, I can only observe the radar. I have no eyes. I cannot see in the sky. Okay, I only have ears. I heard that the radar generated an alarm, which is this event here. Now I'm interested in, is there an aircraft in the sky? Okay, so we have to make use of this above information. Okay, so now let's apply Bayes' rule, which is the following. So P of A given B is P of A, P of B given A, divided by, we are just applying the formula, P of A, P of B given A, plus P of A complement, P of B given A complement. Now, in this situation, our sample space is omega, and we're just splitting into two parts, A complement. So instead of n terms here, instead of having n terms here, we only have two terms here. And they form a partition because A and A complement have got nothing to do with each other. They are disjoint. And A complement, the union is everything. So we are allowed to use the Bayes rule formula, which is this one here, which you should internalize to memory. So you see, we are doing something legitimate. The second probability is 0.01. No, Samuel, you are actually not correct, because you see, that's a very good point. This is not 0.01. I know that you are thinking that these two numbers here must add up to 1. That is a very, very wrong misconception, because here we are conditioning on A and A complement. So we are living in different universes once we have conditioned. So these two numbers don't have to add up to 1, and they shouldn't add up to 1 in general. Okay, so notice what this is trying to say. There is an aircraft present in the sky and the alarm sounded. Here there is no aircraft in the sky, but the alarm sounded. So if the aircraft in the sky and there's no aircraft in the sky, these are completely different situations. These two numbers don't have to add up to 1. Understand? Deng Jie and Samuel, you all have the same common misconception. I also had this misconception at the start. But if you are conditioning on different things, these numbers don't have to add up to 1. Okay. Yes. So what has to add up to 1 is indeed probability of A plus probability of A complement must add up to 1. Okay. But these guys here don't have to add up to 1. Don't have to sum to 1. Very, very important. Thanks for pointing out the Zoom people. Okay, so now it's a matter of number plugging, right? So P of A is 0.05 multiplied P of B given A is 0.99. And we have the bottom, which we copy here. Plus, so we have P of B given A complement, which is 0.1 here. So what is P of A complement? Can someone tell me? This is information we don't have. We don't have this information. Can someone supply it to me in the Zoom or in the lecture room? Perfect, 0.95. Because of this formula that your colleague here mentioned, because we know that this is 0.05, so this must be 0.95 in order for this to add up to 1. Okay, so this is whatever it is, you can put it into a calculator, it's 0.3426. Okay, so this system is not very reliable, okay, because condition on the event that the radar generates an alarm, you hope that, there is a high chance that the aircraft is present, but actually it's not very high, okay. So there's something that is a bit hard to understand at the very beginning, but you need to know what causes what, right? So here, aircraft present causes the radar to generate an alarm or not generate an alarm. Here, there is no aircraft, whether or not it generates an alarm, these don't have to add up to 1. Nothing, okay? This could be 0.0555 if you wish, okay? It doesn't have to add up to 1. Here, we are trying to flip things around by using Bayes' rule, okay? And the important thing here is that A and A complement form a partition of the sample space. They don't have anything to do with each other. They are disjoint. But if you take their union, disjoint, if you take their union, you recover the full space. That's why we are allowed to apply the total probability theorem. And this is where I want to stop today. This Tuesday lecture is very nice. It's a nice and short lecture. And very good. Hopefully all of you understand something. And if you don't, today I have time, you can come and ask me. All right. We have tutorials this week. We have tutorials. I think some people would have had tutorials on Monday, Tuesday. There's one more on Thursday if you wish to come. Okay. The other professor is very, very experienced also. Yeah, so that's good. All right, this is where we will end today. And take care. And I'll see you on the Thursday lecture. Okay. See you. Thank you. Bye-bye. I will stop the Zoom. Bye-bye. Can you come down? Hard to hear.